fundamental working of solar cells, their generation, different types, and different governing parameters, which basically dictate the performance of a solar cell, and we can measure those parameters while while designing a solar cell in a laboratory. So, starting, what is a solar cell? It is basically a conversion device. So, it is a conversion device, and that conversion device means that it directly takes the input and converts it into the output and does not store. So when it is switched on, only then it is able to provide electricity. When it is switched off, then there is no more electricity stored within the device. So it is known as a conversion device. It is not a storage device. So it works on the principle of photovoltaic effect. So what is photovoltaic effect? It is simply taking up the photons from the sunlight and converting those photons into electrical energy. So basically converting sunlight into electrical energy is known as photovoltaic effect into electrical energy. And this is done by a solar cell. So this effect is known as photovoltaic effect. And strictly, if we talk about the fundamentals of solar cells, then solar cells work on the principle of photovoltaic effect. Now, how does this effect take place? In order to understand, we need to consider that how the solar cell, what is the construction of a solar cell? So solar cell has many components. First of all, it has a it has a glass upon which the solar cell is manufactured or deposited in a laboratory, and that glass is known as, it is transparent glass substrate. We call it a substrate. It is a rectangular uh, type of a glass, and it is a conducting glass. To make it, so we call it transparent conducting oxide. We say it oxide because there is an oxide layer coated on one side of this glass. And it can be a fluorine tin oxide or it can be an indium tin oxide, ITO or FTO. So normally we use this kind of a glass, which is very thick and very mechanically strong. And it is basically coated on one side with a conducting oxide, whether it is fluorine tin oxide, FTO, or indium tin oxide, ITO. So this fluorine tin oxide can bear the temperature more than 500 degrees centigrade, while ITO can bear the temperature, cannot bear that much high temperature. It is used for very sophisticated and sensitive devices, while FTO is used where we need to provide temperature treatment while preparing our device more than 450 or 500 degrees centigrade. So the first part of the solar cell is basically a conducting oxide. Upon that conducting oxide, what do we deposit further? We coat it with another layer, uh, which is known as ETL. So the function of this layer is basically to transport those electrons which have been generated by the light absorber when the light absorber is going to absorb the sunlight. And it means when photons are absorbed, they basically are absorbed by the material within the solar cell, which is known as light absorber material. And it will provide electron because it will convert photons into electrons, and those electrons will travel through this electron transport layer, and then they will go to the transparent conducting oxide, and from there they will go outside the solar cell in the external circuit. So after that ETL, we have another coating, and that coating is known as absorber. Light absorber or active material. We also call it active material because this is the material which is going to respond to the sunlight, and it is going to absorb energy, photons from the sunlight, and it is going to convert those photons into electrons. So then we have On the other side of this light absorber material, we have a hole transport layer because that is a semiconductor device. So it means that when photons will be absorbed, they will create electron hole pairs, just as in semiconductor, electron hole pairs are generated. Electrons will travel on this side while the holes will travel on this side. So electrons will travel on this side while the holes or H, we can use symbol H, will travel on the right hand side because they are oppositely directed and they will travel. For example, electron will travel to the positive side and the hole will be attracted toward the negative side. So after this HTL is a layer which is going to support the movement of the hole, just like in a storage device, electrolyte is a medium where ions travel, while external circuit is the medium where electrons travel. So then after that, we have basically, this is a metal contact, we call it, this is the front contact, we call it front contact. This is the front side of the cell. And this is the back, which is kept in sunshine, right? Or which is exposed to sunlight. While the other side of the solar cell is a metal contact. It is made up of pure metal, whether it can be starting from platinum or silver or gold, or even we can use some kind of semiconductors as well. For example, graphene, we can put a carbon layer on it. We can also use certain semiconductors, for example, nickel sulfide, for example, copper sulfide. They have been proven very good back contacts for solar cells. So, but it is known as back contact, right? It is also basically, now this is the structure of a solar cell, right? We call it back contact. As per our understanding, definitely it is basically a device which has two electrodes. One is the positive electrode, or you can say this is known as positive electrode, or this is the anode. However, on the anode, basically our light absorber material is coated. So it is known as photoanode. We can't call it p-type. Rather, we can say that it can be, it is basically p-type in nature, that it is attracting electrons on this side, right? And since light absorber material is always coated on this side, so this material can itself be n-type or p-type. However, it is coated like this. Um, so therefore, this anode is not simply called anode, rather it is known as photoanode, or we also call it working electrode, because in solar cell, because our light absorber is coated on this particular anode. After that, we have HTL and then we have back contact. This back contact is negatively, because this metal is always negatively charged. It can be the n-type, it can also serve as an n-type material, and we can say that this is known as a cathode. So basically, it is a p-n junction device. However, the p-type material is serving as a basically as a photoanode, and the n-type material is serving as a cathode. Now, this is what these are the fundamental parts or components of a solar cell. Any kind of generation, if we talk about, starting from commercial silicon solar panel to fourth generation lab grade device. How basically now photovoltaic effect takes place within these materials, these components. So step one is that light is absorbed. Light is basically, since I am saying that this is the front contact, so it means that this side is exposed to sunlight. This side is exposed to sunlight, and light passes from this transparent conducting oxide to the ETL. It also crosses ETL and it goes directly into the light absorber. And this is the material which is going to respond to this light because it will absorb photons. Neither the ETL will absorb photons nor this glass will absorb photons. Rather, it is the light absorber material which is designed along with this band gap such that it will absorb some photons from the sunlight. And you know that sunlight carries photons in UV region with UV energy, with IR energy, and with 7 colors of light, means that visible region. And the total, you can say the wavelengths present in the sunlight spectrum start from 200 nanometer, which is the UV, to 800 nanometer, which is almost the IR, or beyond IR, right? And you can say that 400 to 800 roughly nanometer also calls for starting from UV to IR region. In between, there are 7 colors of light which correspond to the in-between wavelengths, right? So 400 to 800 nanometer means that this is the visible region of the solar spectrum. And visible region is IR is the lower energy, UV is very high energy, and visible is the moderate energy. So this light absorber is designed either to absorb IR region or to absorb visible region of the solar spectrum. So IR is a 45% of the total spectrum, and it represents very low energy, just correspond to the heat of the sunlight or the warmth of the sunlight, wherever the visible vision carries all 7 colors, and those with the peak wavelength, which is kind of an orange color in 579 nanometer, which is the color of the sunlight, and it it is a moderate energy. This light absorber can absorb energy either in the visible region or in the IR region. And if we say that 100% electromagnetic spectrum of the sunlight, then IR is the 45% of the total, and UV may be 10% of the total, and rest of the percentage of spectrum belongs to the visible region. So IR and visible are almost of same percentage, and they contribute to the electromagnetic spectrum of the sunlight. And this light is going to absorb some kind of photon, some kind of energies. Okay, so our first step is that light is absorbed from the front contact, which is placed in front of the sunlight. And then now what happens in the light absorber material? So it directly goes to the third layer. And here the process begins. In third layer, it is a semiconductor material which has got valence band and conduction band. So light will come, it will be absorbed according to its band gap, and definitely electrons will get excited and they will go to the conduction band. And a hole will be created where the electron is left in the valence band. So it means that electron hole pair is generated over there. Now what happens? Next is charge separation, means electron have to travel to the ETL layer. So our next step is electron hole pair is generated. Electron hole pair is generated. This is the next step as a result of the light absorption. And then internal electric field separates the charges. Now what happens? Basically, look at this structure of the solar cell again. It means that the process begins from the third layer, which is coated on the photoanode, right? So let's look at the photoanode once again. So if this is the TCO, over which we have another layer, which is the ETL, and then we have another layer, which is the light absorber. Let's remain to the confined to these 3 layers. So here the light comes in, and it directly goes to the absorber or the active material, and electron hole pair generation takes place over here. Now, those electrons, there are 2 paths. Electron have to travel to the more convenient path. Okay. Now what happens? Since ETL is also a semiconductor, TCO is also a semiconductor, all are semiconductors, oxides are semiconductors, and this light absorber is also semiconductor, and all have some valence band and conduction band energy values present inside. Suppose this is the band positioning of the light absorber. Okay, these are the energy levels. Now this ETL will definitely be somewhere here. Okay, and this TCO will be somewhere here. So it means that basically it is a wide band gap. It means that if this band gap is suppose 2 electron volt, then this conduction electron TCO band gap will be greater than 2 electron volt, maybe 3.2 electron volt. So it means there is larger distance between the valence band and conduction band uh, energy positions, energy level positions in the TCO. So this is the TCO. And then we have the, sorry, this is the ETL layer. So now I am just considering the energy levels present within these 3 layers. And over here, this is the conduction band edge of TCO. And this is obviously its valence band, right? Now electron is going to be produced over here first of all. This is the light absorber, third in the third material, right? This is the second and this is the first. And this whole makes up our photoanode, right? So light gets absorbed in the third material absorber and it will get excited. It means that electron will move to the conduction band. Now it has to, we will not allow it to go back and recombine. Rather, we want it to go in the outside circuit. So it means that it is more easy to jump over here. So it will go in the conduction band of the ETL. And from here, it will be attracted to this. So it means that if suppose this is negative charge, this is positive charge, right? All energy levels have some, they have potential energies and the difference of potential energy means that there is a potential difference. Mean there is an electric field present between these energy levels. So it means that electrons are traveling through these energy levels. So they will not go and recombine with their corresponding hole. Rather, a charge separation will take place. So it means that now electron is going to jump from this to this, and then from this to this, and then from here there is a copper wire attached or some external circuit, external wiring attached. So it means that it will go outside, right? So this is it means that this was our photoanode, and from here it went to the outside circuit where it ran some load and go back to the back contact and was collected by the back contact and then went back to the, so that was our photoanode. That was our photoanode and that was our cathode. Okay. And this HTL layer will support the holes to travel toward the cathode. It is negatively charged and this is kind of positively charged. So it means that electrons will first move out toward the left side, go into the external circuit, and then come back to the cathode. And from here they will find holes, and those holes will carry them back to this photoanode. Okay. They will keep on jumping within the holes and then get back to the photoanode. It means that the energy will again become available for the photoanode because electrons will return back to the cell after completing the circuit. So this is what is happening, right? So now that was the path of the electrons toward the left side. Wherever the holes, they will also not remain immobile in the light absorber. Rather, if this is the light absorber, then the hole will definitely go to the hole transport layer, and from there it will jump. It will be present over here, and it will not go further to the cathode, or maybe they can go, and the electron will come, or the electron will be collected because that is normally a metal, or it can be a semiconductor as well. Depends upon whatever metal we are using. And those electrons will come back through these holes and come back to the valence band and will again become available for next energy cycle. So this is what is happening, and this is known as photovoltaic effect. And this is the working principle of a solar cell. So it means that each component of the solar cell whether it is a transparent conducting oxide or the electron transport layer or the absorber layer, every component has its own function to provide a path to either electrons or holes, either to liberate the electrons, means to facilitate charge separation and make the electrons to go into the external circuit, and to provide holes a path where they can easily reach to the collector and get the electrons back and take them back to the valence band of the light absorber, so that they are again made available for the next one. Whenever the radiation comes in. So this process is known as energy conversion, solar energy conversion. So now we discuss certain parameters which govern the functioning of the solar cell. Since you know that cell has many layers. So all layers they are basically deposited onto one upon each other, right? And therefore they form interfaces, right? So it means that absorber layer has an interface with the ETL layer. ETL layer has an interface with the TCO. Every interface adds up to the resistance of the cell. And secondly, uh, if those materials have structural defects, point defects, or atomic level defects, so all these defects are also adding up to the resistance of the solar cell. So these resistance, they drop the efficiency and the maximum current and voltage of the cell, and they are known as parasitic resistances. If we are talking about the structural resistances, resistance to the path of the electrons, which is faced due to the structural or crystal defects, those are known as or the interfacial you can say, or the structural defects rather, that is known as interfacial defects, or the means their interfaces are not making proper contact with each other, and they are not properly making interacting with each other at atomic level. There is a poor deposition of one layer on the other. All this corresponds to basically uh, series resistance, right? So it is known as series resistance, right? That is a parasitic resistance which is eating up the performance of the cell. And if we say that the resistance which is present due to the uh, which is corresponding, you can say, towards the recombination process, that resistance is known as shunt resistance, right? So shunt resistance should be high in nature because it should facilitate charge separation and not charge recombination. But series resistance should be low because it will provide a feasible path for charge separation. So it represents the grain boundaries, the structural defects, or the interfacial defects, or even the contacts which are making the cell to connect with the external circuit. So, or the connecting leads, all these add up to, and they are known as RS. And if there is a if the electron is getting resistance in the way of recombination, then that is known as RSH, shunt resistance. Okay, so if we have a diode model to understand an equivalent circuit for the sun, so solar cell, so we say that solar cell is basically a current source. It is providing current to the external circuit, and this is a symbol of a current source because this is a symbol of a voltage source, right? And here it is acting as a current source, means that it is converting photons into current, basically, right? And that current is known as photonic current. So this is the photonic current. Now, how many components are eating up this photonic current? They will be definitely considered as parallel paths. And they are acting as a load on this voltage source. Just consider a series resistance. Just consider a series resistance. A parallel resistive circuit, and all resistances are acting as a load on this because they all have to draw current from this voltage source. So either this voltage source is also a current source actually. So if I consider its role as a current source, then I am making up this symbol. And let us call this is our solar cell, and it is acting as a current source because it is absorbing photons and giving away electrons, right? And this is the photonic current that it gets because this current has been generated as a result of the absorption of photons from the sunlight. Now, how many loads are connected? First of all, it is the internal diode structure. So its internal diode structure is going to draw current, and that current is known as I naught or I saturation current. If there is no light, even then this suppose if we just forward bias this diode, then the current that is going to draw is known as diode current, or the you can say the saturation current. Okay, so normally solar cell, when it is being made forward biased in the absence of light within the laboratory, then it is just acting as a diode, and it will draw only the current that a diode has to draw the current, right? So one path serve for its internal diode kind of structure. Then this is the R shunt. So this is the resistance in the way of electrons, which prevents it from recombination, right? So this is the R shunt. R shunt is also drawing some part of the current, right? And then this is RS. RS, this is a series resistance. This means that R shunt is connected in parallel and RS is connected in series. And then here is our load. Whatever, suppose we are trying to run a bulb using a solar cell. So the leftover current will be given to this external load. So it means it is just like the overpotential in the storage device. That was due to the internal resistance, the cell started uh, storing some voltage instead of giving it away to the external circuit. So it means that this is a diode model in which we say that our solar cell is a current source. It is the symbol for the current source. It is providing, it just resembles as a parallel resistive circuit where this is a mainline current. It is known as photonic current, and it has different paths where it has to give current, and before giving it to the external load, it will provide current within the cell due to its internal resistances. First of all, it will provide current to its diode-like structure, right? Then it will provide current to this shunt resistance, which basically serves as a resistance present between, you can say, the conduction valence band and the conduction band. Since when the electron get excited, it will, after some time, it will de-excite naturally and go back. We don't want this process. We want this electron to forever separate it from this pole and go into the external circuit. If somehow it this electron cannot get separated, and before it goes away, it gets recombined. It means that basically this is the resistance in the path of the electron extraction to the external circuit, and this resistance is known as R shunt. So it means this is the kind of resistance which should be very high. And you know that according to Ohm law, when the resistance is very high, the current is very low. So it means that this resistance has to be very high, because however, this resistance is definitely representing a path which is drawing a current. It means some of the recombination is taking place. However, this is the resistance which occurs due to grain boundaries, due to structural defects, due to interface defects and contacts, all that depends. This is known as series resistance. So it means this is the resistance which the load is sharing in series with it. Okay, and there are how many paths? One is the diode current, which is the saturation current. The other is the shunt, I shunt, and then it is the I load. So it means that for every path, there is a different type of current, but all three currents have to be provided by the solar cell. It is the responsibility of the solar cell to provide. And the two paths, they add to the current losses. It means that all the current that is being generated as a result of the photoelectric effect, photovoltaic effect, is not being provided to the external load. Rather, it is being utilized by two other paths as well. One is the shunt resistance path, the other is a diode path, and then it is the RS resistance, which is also sharing. It means that this load has also some resistance. However, this RS is also adding up to the resistance. So it means that if RS is high, obviously it will drop current more. And this whole equivalent circuit is going to represent basically the working of a solar cell. So this is the basic working of the solar cell.